Hi, I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. I'm currently building a full-stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it in that way, and what I do differently. Today, we're going to be getting into asynchronous system design for my e-commerce platform, Outbox, Idempotency, and what I'd add at scale. Without further ado, let's continue. There is a moment in every checkout flow where the order is created, the payment is confirmed, and then you need to do a bunch of things that shouldn't block the response. Send a confirmation email, update analytics, provision access to a digital product. If you do any of those synchronously, you have two problems. First, latency. The user is waiting for SendGrid, waiting for your analytics database, waiting for your license key generator. Every extra step adds response time. Secondly, and more importantly, availability coupling. If SendGrid is down, your entire checkout fails. The customer can't complete their own purchase because an email service is unavailable. Async decoupling breaks that dependency. The checkout returns immediately. The email goes out when it goes out. SendGrid being temporarily unavailable is a delay, not a failure. This video is about how I handle asynchronous operations on my platform without a message broker, an Outbox pattern with a cron job, Stripe webhooks with idempotency, and the principles that keep asynchronous operations correct when things fail. The synchronous limits. Every synchronous system has a structural ceiling. It's a coupling problem, not a performance problem. Latency coupling. The caller's response time is bounded by the sum of all callees. 3 services at 200 milliseconds each, 600 milliseconds minimum user wait. The availability coupling. If any callee fails, the caller fails. 5 services at 99.9% availability gives you only 99.5% combined. Roughly 44 hours of downtime per year during which customers cannot purchase. At $100 average order value and 100 orders per day, that's approximately $4,400 in lost revenue per year from availability coupling alone, before accounting for customer trust damage. Throughout coupling, the caller can't sustain more requests than the slowest callee can process. Async addresses all 3 by decoupling producer and consumer in time. The producer writes to a durable intermediary and returns immediately. The consumer processes at its own speed. If the consumer is down, messages wait. If the producer bursts, the queue absorbs it. The producer's availability and the consumer's availability are now independent. The Outbox pattern. The fundamental async correctness problem. How do you guarantee a side effect happens if and only if the primary operation commits? Without the Outbox, write to the database, then publish an event. The server crashes between those 2 steps. If the server crashes between those 2 steps, the database write committed, the event was never published, the order exists, the confirmation email never sends, inconsistent state. The Outbox pattern. In the same database transaction as the order write, insert a row into the email Outbox table with the status pending. Both writes are atomic. If the transaction fails, neither write happens. No orphan email queued. If it succeeds, the Outbox row is durably stored and will be processed. A cron job polls the Outbox every minute. It selects pending rows with available at less than or equal to now. Dispatches the email, marks the row sent. If the email call fails, the row is available at is pushed forward with exponential backoff. One trade-off worth naming explicitly. 60-second polling means up to 60 seconds of delivery latency. For a confirmation email, that's fine. For access provisioning to a digital product the user is actively waiting to download, 60 seconds might feel like a broken purchase. The polling interval is a design decision, not a given. Use PG Notify to trigger the cron immediately after commit if certain entries need faster processing. One transaction, order, and Outbox row. Inside one database transaction, the order row, the order item, the payment attempt record, and the email outbox row. All 4 writes succeed or all 4 roll back. No intermediate state. This is the same transaction from the state machine video, the one that transitions pending payment to paid, now with an outbox row added. The state machine guarantees the order reaches a valid state. The outbox guarantees the side effect is durably queued. Both happen atomically in the same commit. The cron job design has 3 important properties. Polling gap. 60-second polling means up to 60 seconds of delivery latency. Acceptable for email, potentially not for access provisioning. Select for update, skip lock. This prevents 2 concurrent cron workers from processing the same row while distributing work across different rows with no thundering herd. Provider idempotency key. If the cron crashes after sending but before marking sent, the next rerun processes. The provider's idempotency key prevents double delivery. This is the second layer, not the primary protection. The lock is primary. Delivery guarantees. 3 delivery guarantees in asynchronous systems. You have to choose one. At most once. 0 or 1 deliveries. No redelivery on failure. Possible message loss. Used for telemetry and metrics where losing one event is acceptable and duplicates cause more problems than losses. At least once. 1 or more deliveries. Redelivery on failure. No message loss. Possible duplicates. This is the correct default for business events. A loss order confirmation is unacceptable. Effectively exactly once. At least once delivery plus idempotent consumers. The consumer may process a message multiple times, but the side effect happens once. True exactly once, where the broker guarantees no duplicates without application help. It is impossible in distributed systems. This is the 2 generals problem. My platform uses at least once. The critical implication that catches developers off guard is at least once means every side effect your consumer performs needs its own idempotency mechanism, not just the database write, but every external call. If your cron job sends an email and then writes to the database and it crashes after the email sends, but before the database write, the next run sends the email again. The database write being idempotent doesn't protect the email send. Each side effect, email, analytics event, access grant, audit log, needs its own idempotency check. Idempotency. 2 patterns in practice. 2 idempotency patterns in my platform. Stripe webhooks. Each webhook carries a unique event ID. I store it in order events with a unique constraint. When a webhook arrives, the handler attempts to insert a row with the event ID inside the same transaction as the state update. If the event ID already exists, the unique constraint rejects the insert. Even if 2 concurrent webhook deliveries both pass the application level check, only one insert can succeed. The database enforces this atomically. Email outbox. The cron job uses select for update skip lock to lock the outbox row before processing. This prevents 2 concurrent cron workers from claiming the same row. The provider idempotency key, a hash of the order ID and the email type, is used if the cron crashes after sending but before marking sent. The lock is the primary mechanism. The provider key is the second layer. At scale, I'd add processed events table, a general purpose idempotency store recording every successful process message ID checked in the same transaction as the side effect. This pattern scales to multiple consumer types processing from multiple queues. Commands versus events. They're not the same thing. So commands and events are not the same thing. Conflating them produces real bugs. A command requests a state change named in the imperative. Send email, process renewal, provision access, single intended customer. Exactly 1 worker should process it. The sender expects a result. The sender knows the receiver. An event records that something happened. Named in the past tense. Order placed, email sent, access provisioned. Many potential customers, fan out to email, analytics, audit. Immutable. The publisher doesn't know who listens. The bug, routing a command to a pub subtopic. If process payment is published as an event, and multiple payment service instances subscribe. Multiple instances process it simultaneously. The customer is charged multiple times. Commands go to work queues with competing consumers. Events go to pub subtopics with idempotent subscribers. The naming convention is a practical enforcement mechanism. Commands use imperative verb noun. Send email. Events use past tense, email sent. If you enforce this convention in code review, violations become visible immediately. A past tense message routed to a single consumer or an imperative message broadcast to multiple subscribers triggers a conversation before it reaches production. Choreography versus orchestration. When multiple asynchronous steps need to coordinate, the question is whether they do it through shared events or through a central coordinator. Choreography is decentralized. Each service reacts to events independently and publishes its own. No central coordinator. Adding a new consumer requires no changes to existing services. Good for simple, independent reactions with no conditional branching. Bad for debugging. Why didn't this customer get their license? Requires querying every participating service and reconstructing states from their individual records. Orchestration uses a central process manager that knows the full workflow sequence. It issues commands, waits for responses, and handles failures. It's required for multi-step workflows with conditional branching or compensation logic. The observability difference is what makes orchestration preferable for business-critical workflows. With orchestration, the process manager holds the current workflow state centrally. What is the state of this order's async processing? Is answerable with one query to the orchestrator. For support tickets and incident responses, why didn't the customer get their license? That difference is significant. My platform today, simple server action, single database transaction, one async side effect, no coordination needed. I'd add orchestration when checkout spans multiple idempotent services with their own failure modes. Sagas. Distributed workflow consistency. If I decompose into a multi-service checkout, I'd need Sagas. A saga is a sequence of local transactions where each step publishes an event. If a step fails, the saga executes compensating transactions to undo previous steps. A classic example is reserve inventory, charge payment, create order, send confirmation. The payment fails, release the inventory reservation. Every forward step has a defined undo. Some operations have no clean undo. Sending an email cannot be retracted. The design principle that makes Saga practical: put irreversible operations last. If the email sent is the final step, no subsequent step can fail and require the email to be undone. Structure your saga so that everything that can be compensated comes first. Inventory reservation, payment hold, order creation, and everything irreversible comes last. Email send, notification dispatch, analytics event. I don't need sagas today. My checkout is one server action. If I decompose into services, the principle is the same as Outbox. Atomic within a service, eventual consistency across services. Today versus what I'd add with a message broker. When my platform outgrows the cron-based email outbox, I'll add a message broker. The evolution: Outbox relay process publishing to the broker with at least once delivery. Idempotent consumers with a process events table checked in the same transaction as every side effect. Dead letter queues per consumer with depth alerting. Consumer lag monitoring as the primary health signal. Pub subtopics for fan-out events. Work queues for competing consumers. One cost worth naming before adding a broker: event schema evolution. Once you publish events that multiple consumers depend on, the event schema is a contract, exactly like the API contracts from the first video in this series. Adding a field is usually backward compatible. Removing or renaming one is a breaking change that requires either versioning the event schema or coordinating all consumers simultaneously. A message broker is easy to add. It is not necessarily easy to evolve. Schema stability becomes a contract commitment the moment your first external consumer subscribes. Async decouples producer and consumer in true time. The Outbox pattern writes the side effect to a durable Outbox table in the same transaction as the primary operation. Cron polls committed rows. Atomicity guarantees by the database, not the application. At least once equates to every side effect needs its own idempotency, not just the DB write or the email send, the analytics event, or the access grant. Each need its own idempotency check or the crash after send problem recurs. Commands, work queues, one consumer, events, pub sub topics, many consumers. Routing a command to pub sub causes double processing. Enforce with naming, imperative for commands, past tense for events. Orchestration for business critical workflows. The process manager holds workflow state centrally. Where is this order is one query. Choreography for simple independent reactions. Event schemas are contracts. Once consumers subscribe, adding fields is safe. Removing is breaking. Designed for schema evolution before adding a broker. Same discipline as API contract. For a client, async side effects on this platform uses the Outbox pattern. Email dispatch is written in the same database transaction as the order, guaranteeing it will be processed. The email Outbox is pulled by a cron job with skip locked, preventing duplicate processing. Stripe webhooks are idempotent via unique constraint on event ID. I'll flesh out thoughts. I love fleshing out thoughts for extended periods of time. I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're designing asynchronous workflows for your own platform, Outbox patterns, idempotent strategies, or the path from cron-based to broker-based processing, reach out. I'm open to freelance projects and consulting. The full post is linked in the description. Complete Outbox implementation, the skip locked cron pattern, the idempotency table design, and the decision table for choosing between choreography and orchestration. Next in the series, concurrency, race conditions, select for update, and idempotency keys. I'll see you there.